Hello and welcome to this short tutorial for working out the second moment of area for the sector of a circular annulus, or as it's also known, a flat disk. As I sort of go through this, I'm just going to refer to the sector of the circular annulus as just the annulus, because it's a bit of a mouthful saying the full thing every single time. So before I start getting into the calculations and the derivation, I wanted to just give a brief overview as to where this can be important. One area where I've come across this in the past is with cold form steel, which is where you get sort of a flat bit of steel and you send it through a bunch of rollers and you form a profiled section that's used all throughout structural engineering. An example of this can be seen in this diagram here on the PDF, and you can get this PDF from my website if you want to have a look through. It has all the formula derivation and everything, so it would be quite useful as well to have this for yourself. But on the first page it gives an overview, but it also shows this channel section, and this is sort of a typical cold form section that you'd normally see. You see these get used for wind posts, for stud work, even some structural members end up using channel sections. And you'll notice that these corner bends here are effectively this annulus section that we're interested in. Effectively, it's a chunk of a flat disk in here. You can see this zoomed out view over on the right here with this yellow region sort of highlighting the area that we want to look at. And in particular, we want to know the second moment of area of this, because when we're working out the sectional properties of something like this channel section, we need to know the second moment of area about the local axis of this annular sector, this annulus that we've got. So I looked online and there wasn't a lot of good information on how you derive this. You basically have to derive it from first principles. So I wanted to put this together to sort of aid engineers, give them formulas and give them a method of dealing with this, so they don't have to go through all the legwork and all of the painful calculations to work this out. So in order to do this, I've sort of set up, there's a two-stage process I've set up to go through. You first work out the second moment of area for the annulus in a sort of simplified case, and then you apply a global rotation to that simplified case to deal with the general case. So it greatly simplifies the problem into sort of two steps, and sort of simplifies a lot of the mathematics as well, which is obviously helpful. So I'm going to jump into that now. The following page after this sort of introductory page on the PDF has sort of overall dimensions that we'll be using to derive the things that we want. So this diagram you see here, we have effectively two sectors of a circle. We have this red sector, which is this small area in here, and then we have this blue sector. Now the blue sector, you can't really see all of it because it's hidden by some of the red sector, but effectively what I'm saying is the blue sector goes from this point down here all the way up to the edge of the circle. So you can kind of think of it as the blue sector kind of overlaps the red one. It's kind of hard to show it on this diagram, but I have mentioned it in the text and the write-up. So these two sectors, they are defined by an outer radius, this RO for R outer, radius outer, and this inner radius, which is denoted by this RI input variable down here. So that sort of lets us define how big these circles are, how big these areas of these sectors are. We also want to know the bend angle of this, and the bend angle we're going to call theta over here. And you'll notice that there's an alpha angle as well. The alpha angle is just half of theta. And what I've done as well, and this is very important because it simplifies the mathematics, I've actually centered these sectors on the x-axis. So you'll notice that you've got a line of symmetry along the x-axis here, which greatly simplifies the mathematics. In particular, you'll notice that the centroids of this red sector, the centroid of the blue sector, and the centroid of the annulus, which is this hatched, black hatched region, those three centroids all lie on the same line. They all lie on the x-axis. And you'll see that noted here. This little red icon is the centroid of the red sector. The little blue icon is the centroid of the blue sector, and the little black icon is the centroid of the annulus, the hatched region, and that's the one we want. Okay, so that sort of sets up our problem to start off with. This is the simplified problem that we're going to solve first, and the way we're going to solve this first is we're first going to find this the location of this black centroid, the centroid of the annulus, the hatched region, and then we're going to use the position of that centroid to work out the second moment of areas about the x and the y axis for this annulus, for the hatched region. Okay, so step one is finding this centroid, and the way we find this centroid is we use the process of geometric decomposition. And effectively what we're going to do is we're going to, if I scroll down here, we're going to find the centroid by doing the large sector minus the small sector. Okay, and in particular the geometric decomposition is this formula here in sort of a generic sense. It's the sum of the area of each subdivided element times by the distance to the centroid of that subdivided element over the sum of all the areas. Okay, so what we can think of that, if I just draw this sort of briefly in here, we just do a new drawing. We have the blue sector like this, which has a centroid. We have the red sector, which is smaller, and that has a centroid over here. And then we have the annulus, and that has a centroid over there. And what we're doing is we're doing this effectively in terms of a sum, and we know the area of the blue. The area of this is going to be A large. We know the area of the small sector, A small. We can work that out using our sort of circle formulas because we know the angle of this bend, and we know the radius, so we can work out the area of these two sectors. We also know the distance to the centroid. This distance here is going to be A large, and for the small sector that's going to be x small. Now you may be asking me, how do we know this x large and the x small? Well, I went online and I found a formula, and that formula is this one here. So 2r sine alpha over 3 alpha, and you'll remember the alpha is just that smaller angle that we mentioned before. The r is just the radius that we're looking at in question. So if you want to find the centroid of the large sector, that r would be the outer radius, and for the centroid of the small sector, that r would be the smaller radius, the inner radius. Okay, so what I've done here in the table below is I've written out the formulas for each part that we need. So we've got the areas and we've got the distances to the centroids, and so now all we have to do is apply our geometric decomposition via this formula, and we can work out the distance to the centroid of the annulus. So to be clear, if I just do a little dashed line, that's our 0, 0 point over here. This dimension, that is our x annulus. Okay, probably misspelled annulus, but you get the idea. And so all we're doing is we're doing these two multiplied together plus these two multiplied together all over the sum of these two. Okay, now what you'll notice as well is that when we're doing the sums in here, we're dealing with a negative area here. This negative symbol is important. You'll see on the spreadsheet here, you've got on the PDF, you've got a large times x large minus a small times x small, because we're wanting to subtract this red sector from the blue sector, and that minus repeats again on the bottom of the fraction. Okay, so it's a little bit to bear in mind there in terms of how we're doing our geometric decomposition. So that's a sort of generic formula. What I've done on the row below here is I've basically just substituted each one of these formulas from the table above into this formula, and then I've simplified all of it, so you've got a nice neat formula for the distance to the centroid along the x-axis. Okay, so we've got that now. Now we can apply the parallel axis theorem to work out the second moment of area. And now to start off with, I'm going to do the more difficult axis. So we're going to start off with the y-axis. So this is our annular sector. we're going to work out, that's xx and yy, we're going to work out the stiffness around this axis, which is going to be our iy of the system. Okay, so to do that, we need to know the distances. Hold on a second, I believe I may have got that wrong. Sorry, it is the other axis, I think. Yeah, sorry, I had the right Cartesian. IY is about the IY axis. Apologies. We're working out this one first, and we'll work out the other one second. So it's around the second amount of area around the IY axis is what we're going to work out first. Okay. So how do we do that? Well, we apply the parallel axis theorem, and the parallel axis theorem, I'm just going to write it out quickly for you, is the sum of I plus the sum of A times x bar, or x bar squared. Let's call it that. Okay, that's in a bracket. So you may be wondering what each of these bits are. Well, this I, we can get this from a formula. I'll show you the formula in a minute. This is the formula for each subdivided element. So the I value of the sectors, the circle sectors, the blue and the red sectors. This A is just the area of the sectors, and the x bar is the distance from the centroid of the overall system to the centroid of the local element. So if I just draw that quickly for you, do another sketch. We have our overall system. So that there in black is the centroid of our annulus, the overall system. Then let's say we have a centroid of the red circle sector. We have the blue would be the centroid of the blue sector, and our distance that we want, our x bar, remember, our x bar is going to be this distance and this distance. This one here is going to be x small. This one here is going to be x bar large. And we don't care which one we subtract from the other when we're doing this calculation, because we're going to square this as in the formula. So we don't care about the sign, whether it's negative or positive for this. Okay. And so in the table below, I've actually written all of this out for you. So this sort of nasty looking formula is to work out the I value for the circular sector, for a large and a small sector. And then the table below sort of splits it all out. So we have the I values for the large and the small circular sector. We have the cross-sectional area of the large and the small circular sector. And then down here, we have the distance, the distance from the centroid of the overall system to the centroid of the local system. So these two bits here, these formulas that I've sort of shown and then shown in expanded form, those are these dimensions here. Okay, that's what we're doing there. And then we apply the parallel axis theorem down the bottom, because we now have all of our input values that we want. So we have the parallel axis theorem, which is this one. So that's the sum of I. The I large minus the I small is the sum of the I. Notice we have the negative bit in here again, because we're doing the large sector subtract the small sector. And then we have this bit here, which is the lever arm distances part of the parallel axis theorem. So we have the area of the large sector times by that lever arm distance. So it'll be this distance, the I large, squared, minus the area of the small sector times by the lever arm distance for the small sector. And the lever arm distance for the small sector is that distance there. Okay, and you'll notice the squares in here, so we don't care about the sign. And also notice we have the other subtraction in here, because again we're subtracting the small sector from the large sector. Okay, so we have this parallel axis theorem formula, and again I've just substituted the formulas from the table above, which are sort of written in expanded form. I've substituted all the things in the table above into this formula, and then I've expanded it out and I've simplified it to make life easy for people that want to use these formulas in their own work. So this horrible looking formula down the bottom is basically a simplified version of this one up here when you've put all the expanded forms into it. And I've sort of shown you which parts of the formula are which. So this first part of the formula, that's the I large minus the I small, and then this second part is the lever arm distances part of the formula. So that gives us our second moment of area about the y axis locally for this local simplified situation. I'm now going to work out the second moment of area about the x axis. So just to be clear, we have our sector, that's going to be our x axis, that's going to be our y axis, and so now we want the second moment of area about the x axis. So this is our ix that we have. Okay, and now for the ix it's a lot simpler, and the reason it's a lot simpler is because the centroid of all of the subdivided areas, they all lie along this x-axis. Okay, so our lever arm distances are all going to be 0. All we have to do is work out the I of the large circular sector and the I of the small circular sector and subtract the two. Okay, and I've given a formula for both of those. So if we go to the following page, this is the formula for the second moment of area about the x-axis for the circular sector. And so all we need to do is work this out for the large and the small sector and subtract the two. So I've actually done sort of the full expanded version of this in the table below to sort of illustrate what's going on. But we have this formula here, which is just this one up here, the I value of the large and the small circular sectors. We have the cross-sectional area of the circular sectors. This is not going to matter in the end. And then we have our lever arm distances. As I said before, they are 0 because all of the centroids lie on the x-axis. And so when we basically do our parallel axis theorem at the bottom, these lever arm parts here all drop to 0 because the y large and the y small are both 0. So this all drops out, and all we have to do is this simple subtraction at the beginning, the I large minus the I small, which simplifies to this. I've basically substituted again and I've simplified the formula. So we now have the Ix and the Iy for this annular sector. Okay, but the issue is we only have this about a certain rotation. So as I said before, this is the simplified case when our sector is like this, or I guess we could have a smaller angle like that, or we could have a bigger angle like that. But in any case, all of these situations, they're all basically mirrored around the x-axis. Every single time we always have the annular sector centered or mirrored on this x-axis. Okay, and what we want is we want to be able to have the second moment of area for any rotation of this system. We want to be able to have, the second moment of area of it maybe up here, or maybe down here, or over here. Okay, and so the way we do that is we just apply a global rotation to our I values to work this out. And so what I've got on the next page is this basically worked through. So we have in pink, this is our original annular sector. This is the one that we've worked out before on the previous pages. That's mirrored about the x-axis. And then we have this grey hatched region, which is an annular sector that we'd want for like a global rotation. So this is the sort of the general position that we want. And so all we need to do is we need to know the angle between these two and then apply global rotation to it. So this angle beta in here is our sort of global rotation of the pink area into this grey area. Okay, and if we know this angle beta, we can basically work out our I values for this rotated annular sector. And the formulas on the following page do that. So the formulas, they look kind of horrible, but they're actually not too bad. So the Ix dash and the Iy dash, those are just the second moment of area values that we worked out on the previous pages for that simple case, effectively for this pink outline. Okay, so we know these already, we've worked them out before. The beta is just the input angle for that global rotation. It's measured positive from the x-axis. So in this example here, this beta would be sort of, I guess, positive 60 degrees, it looks like, something like that. So that would be our beta. And then this bit at the end of the formula, this product of inertia, this I dash xy, this product of inertia is always going to be 0 because of the symmetry of the system that we set up by positioning this on the x-axis in the way that we did. So because that's always 0, this bit of the formula drops out at the end, and we're just left with the bit at the beginning, which is we've got all these input variables, we've all worked them out previously. So we can just plug our numbers into this, and it will give us the ix and the iy for this rotated system, for this grey system here. And I should be clear as well that these second moment of areas are always local to the annular sectors that we're looking at. So if I just look at this pink annular sector, the second moment of area for the pink one, I'll just draw this out again just to be explicit here. This is the centroid in pink. The second moment of areas are about this centroid. So let's label that IY, XX. That was our XX, IXX, and that was our IY. Okay, they're local to this centroid of it. They're not local to this 0, 0 point over here. Okay, and a similar thing is true for the rotated system. So we have our rotated system. Let's just draw our Cartesian coordinates. I'm going to draw this one in the rotated thing in a different colour. Let's draw our rotated system. Okay. Let's say the centroid of our rotated thing is there, roughly. We have a local IX and an IY. That's going to be XX, YY, and our IX is going to be around here, IX dash, and our IY is going to be around here, IY dash, or a similar notation that you're using. Okay, it's local to the centroid. It's not around this point, not around the centroid of the, not around the 0, 0 point. It's about the centroid of the annulus. Okay, very important to bear that in mind. And the reason this is done this way and derived this way is because if you know the I value about the centroid of the system, you can then use this to build up more complex geometry and work out the second moment of area for something like the channel section that you saw before. For the channel section that you saw before, you would have something like rectangle, corner, rectangle, corner, rectangle. You'd get centroids of all of these. You'd work out your neutral axis, or your centroid of the whole system. The centroid of the whole system would be roughly around here, and then you'd basically do the second moment of the parallel axis theorem again to work out the I value of the whole thing. So we know the I value locally of this one, we know the I value locally of this one, we know the I value locally of this and this. For the rectangles it's b d cubed over 12, where that is b and that is d. And then our lever arm distances would just be from here to here, or here to here. That would be 0 for the middle rectangle. That would be our y there and there. So we can basically apply the same parallel axis theorem, the the sum of I plus the sum of A y bar squared, where the A is the area of each subdivided element, the I value is the stiffness about the centroid of each of these elements, and then our y bar are these distances I drew from the centroid of the overall system to the centroid of the local system squared. So it's the same thing again, it's just expanded out to a more complex geometry, and that's why it's useful to know the second moment of area locally around the centroid of the annular sector. Okay, and then the last thing I'll just tell you is at the bottom here I've also provided a formula to work out the centroid in this rotated state, and this is just simply using a right angled triangle to work out that position. And just to be explicit here, just to fully finish this off, we have our x and our y axis again, xx, y. We have our typical case, that's our centroid, and we know this distance, this is the distance to the centroid, annulus, x annulus. We have a rotated system up here with a centroid there. The centroid is going in the same position, it's just rotated round. We know this rotation, that rotation is beta, and so we can work out that distance and that distance. They form a nice right angle triangle for us. So that distance there is just going to be the x annulus times by sine beta, and this distance is going to be x cos beta, which is what's written on the PDF down here. So that's where it comes from. So that's sort of how the PDF is, how it's all been derived and how it's all been shown on the PDF. I've also provided an Excel sheet which lets you look at the formulas and get a bit more intuition. The Excel sheet is split up into two sheets. So the first sheet lets you basically type in all your inputs that you would have on the PDF and see sort of what's going on. So you have the radiuses of the outer and inner circles in here as an input. You have the area of the annular sector, and you have the global rotation. And then over here you can see it being plotted. So the dashed part of this diagram, that's the special case, the simple case that we solved, where the thing is centered on the x axis. And then in black we have the rotated form of the situation. And then down below here, in terms of these numbers, we have the area of our annular sector, cross-sectional area. We have the local geometry, so we have the distances to the centroid for this grey system. We have the I values in the x and the y, about the x and the y axis of this grey sector here, grey annulus. And then for the global geometry, it's the same thing, but it's for the black annulus up here. And again, I should reiterate, these I values are local to the centroids here. And you can see the centroids being plotted with these little crosshairs. So the IX local, the IY local is local to this grey crosshair, and the IX global and the IY global is local to this little black crosshair here on the diagram. Okay, so that lets you plot this, and you can change the inputs in here. I'll just sort of show you, make this a bit bigger, do a 90-degree bend, change the global rotation, let's do 180, flips round. So you can change all of that on here. And then also I've done a plot which sort of shows what happens when you vary the bend angle. So when we vary this angle from sort of 5 degrees up to, you know, let's say 270, oops, up to, so when we vary the angle basically, let me do 90. Okay, so this sheet here sort of shows what happens when you vary that bend angle. And what we have here, this table here is just all formulas, so just you can look at the data, but you don't have to mess with it. We've got some inputs up here, so we can change the radiuses again, and then we can change our global rotation of the system. So the global rotation, as we've seen before, is the rotation of the system here. As you can see, I'm changing it here just to sort of visualize what's going on. Okay, so that's the thing we can set as like a static variable here. And then the table below is basically varying the bend angle. So it's varying this angle here, right? It's varying this angle, okay? And it's plotting the results in this chart on the right here. Now, the dashed lines on this chart, those are the second moment of areas for the simple case, for this grey system, this grey annular sector. The solid red and blue lines are the second moment of areas for this black system over here, okay? And what you'll see, you can actually toggle this value up and down. You can change the global rotation. So you'll see that if I set the global rotation to 0, put it in as 0, you'll see that the global and the local perfectly overline, which is basically like saying if I just put in this as 0 in here, oh, sorry, let's do 15 and put in 0 in there, the black outline perfectly overlays with the grey outline, okay? So that's what that system is in here. And if I toggle these up and down with using the arrows, it basically just changes that angle, and you can see how our stiffness changes as we move around. Okay. So it gives you a bit of intuition to how the sort of stiffness changes with the different rotations and everything. And also I should mention as well, if you go into Developer, Visual Basic, and then go into Functions Geometry over here, you've got all these functions, which is basically the written forms of all the stuff in this PDF. So if you wanted to, you could just copy these out and use them yourself, these custom functions. So I've got, you know, the area, centroid and whatnot, and you'll see it on the spreadsheet they're used over here. So these functions are called up in here. So you want to grab them out of there and use them yourself, you're free to do so. Okay, and that's pretty much it. I hope this was helpful, and I'll catch you in the next one. Okay, bye bye.